This is section 3.4, and you recall in section 3.3, we worked a problem where we were crossing a river and looked at resolving forces, vector forces, and so forth. And I want to work in this section a practice problem having to do with projectile motion. And our projectile motion is going to be done in the following way. Again, we're going to take an x direction here, a y direction here. And we're going to throw this object like a baseball with a velocity which is 5 meters per second. Not particularly fast. In case you're curious, the speed with which a baseball is thrown is between 90 and about 90 or 100 miles an hour for a very fast pitcher. We're going to take this angle theta to be 25 degrees. And now what we want to do is set up this problem and see if we can solve it. You'll notice that first of all, we want to resolve the velocity. The force is resolved. We know what the force is. It's straight down in the negative y direction. But the velocity has to be resolved into an x and a y component. Let's first write the acceleration. The acceleration is going to be in the x direction, 0. And in the y direction, it's going to be downward, a minus 10. Okay, that gives us our initial acceleration and acceleration all along. What's our velocity initial? Well, our initial velocity is going to be this 5 meters per second projected in this direction. So that's going to be velocity initial times the cosine of theta. This is going to be velocity initial times the sine of theta. So this is going to be 5 times the cosine of 25, comma, and that's going to the right, so it's positive. This going up, so it's positive. It's going to be 5 times the sine of 25. That gives our initial velocity. What's our initial position? Well, let's say we start from the origin, 0, 0. And now we know the state of the system. You remember the state of the system is when we know for one particle what's its initial position, what's its initial velocity. Then we can solve the equations for that if we know its acceleration, or equivalently, we know the forces that are on it. Okay, so what are those equations? Equations are x final equals x initial plus initial velocity times time plus 1/2 acceleration times time squared. Velocity finally is equal to velocity initial plus acceleration times time. Acceleration final is acceleration initial, so it doesn't change. Now we have to apply these equations in both the x, the y, and if we had it, the z direction also. We've only got the x and y direction. So how do we do this for the x coordinate? Well, we can say that x is equal to 0 plus 5 cosine 25 plus the initial velocity times time, plus, in the x direction, what's the acceleration? 0. So we can see that the velocity in the x direction is just proportional to the time. It moves uniformly along, never speeds up, never slows down, starts from the position of 0. How about the velocity in the x direction? The velocity in the x direction starts out with a value 5 cosine 25. That's its initial value, 5 cosine 25, plus its acceleration times time, which is 0. So that never changes. Acceleration in the x direction is 0. Okay, that gives the x equations. Now what about the y equations? Well, in the y direction, y is going to be equal to your initial y, which is 0, plus your initial velocity in the y direction. It is thrown upward, so it's 5 sine 25 times time plus 1/2 at squared plus 1/2 the acceleration, which is minus 10, times t squared. We can write that out a little bit better here. It's 5 sine 25 t minus 5 t squared. I just took the 10 divided by 2, put the minus sign in front. So that's why velocity in the y direction is going to be 5 sine 25, it's in the y direction, plus acceleration times time. Acceleration is going to be minus 10 times t. So we could write that as minus 10t. Acceleration in the y direction is going to be minus 10, period. So now we know the components of x and y, velocity in the x, velocity in the y, acceleration in the x, acceleration in the y. And from those, we can compute anything else. Now, what is it that's special about projectile motion? Well, at the very top, let's look at what is special that you always want to remember. Number one is the acceleration is always down, and it's minus 10. Even at the top of the motion, the acceleration never goes to zero, it never changes. The next thing that happens is the velocity at the top in the y direction is equal to 0. This object will go upward, stop at the top, turn around, and come back down. When it gets back down to the same height as before, y ground again, it's going to be equal to the negative of the velocity of the ground originally. And since we threw this from a zero altitude, it means at time 0, this is where we start out at 5 sine 25. When it hits the ground again, the y component is going to be 5 sine 25. So those are important things to remember. Then also remember you have this important equation of velocity final squared minus velocity initial squared is twice acceleration times the distance. And that can be very useful when the time is not involved there. So what all could we work from this? Well, there are a number of things that we could work. I'll be kind of moving this around as we work on these. Here are the questions that are always asked. After you set this up, then you can compute anything. What are these special things? How high does it go? In other words, we want to know how high does it get? If you throw this baseball at an angle, how high does it go? And then, how long does it take to get to the top? How high to the top? How long does it take to get to the top? Let's work those two problems and see how we set them up. Remember how we got this far now. If I just look at the y direction, that's the critical part here. What's going to happen when I get to the top? The thing that indicates the top is the fact that the velocity in the y direction stops. It's 0. Well, what is the velocity in the y direction? It's given by this equation. So what do we know? We know that 5 sine 25 minus 10 times t is equal to 0. Well, you can figure out when it gets to the top then. This is at the top. This is time to the top because this says that that original velocity is slowed down to 0 by the acceleration. And so what would we have? Bring this over here, divide through by 10, solve for the t. We get t at the top. Time to the top is going to be 5 sine 25 divided by 10, or 1/2 of the sine of 25 degrees, which I will let you work out. Well, that gives us the time to the top. The next question you could expect on a test is how long does it take to fall back down to the ground? It turns out that the time that it takes to go to the top is the same as the time it takes to come back down. So the time to top and back to the ground is going to be twice as great. So it's going to be 2 times 5 sine 25 divided by 10, or the sine of 25 degrees. You'll notice with that I haven't converted these to numbers. And a lot of times that's really nice, because here you can see that I'll take 2 times 5 is 10, divide by 10. I don't have to mess with all those decimal places, doing a lot of calculations with the calculator or by hand, where I might make a mistake. By keeping it this way, I can simply now say, oh, the total time in the air, going up, coming back, is sine of 25. You'll notice the units are right there too. What else might I want? How far did it go? Well, if I think about this projectile, I want to get how far it goes to how high does it go up to the top, then I can compute that by looking at the distance to the top, and I could plug that same number in. We know what the time to the top is. I could plug it in here and get y to the top. There's a faster way to do it, so I can use this right here. Why? This is a good way to find how far it is to the top, because we know the velocity at the top finally is 0. So we can write this as 0 squared minus velocity initial. What was your velocity initial? 5 times sine of 25 squared. That's going to equal to twice the acceleration times the distance to the top. So the acceleration is negative, incidentally. That negative sign cancels this negative sign. So what I get is s to the top, distance to the top, is going to be equal to 5 sine 25, quantity squared, divided by 20. And that'll tell me how far it is to the top. You can say, how far did it go? Well, that's a little bit more complex. We need to know how long it was in the air. Here you have to make sure you don't use the wrong time. This is the time to the top. It's going to be halfway along its path when that happens, when it gets to the top. It's only halfway. So if you use this number, you're going to get this distance here, not this whole distance. We want this whole distance. How do we get that? We get the whole distance by using the time to the top and back, which is going to be sine of 25. Now, how does that work? Well, we know the velocity in the x direction, and so the distance in the x direction is the velocity times the time. So we can write x is equal to 5 cosine 25 times the time. It's going to keep going, and that's going to be sine of 25. Very neat. Just multiply that out, that'll tell you how far it went. So this projectile motion is really a very standard problem. It verifies that you can understand how to identify that the acceleration is always constant, that the velocity at the top is 0, the velocity is the same when I get back to the ground, and things of that nature. There are a large number of problems that you can work with all of this, and so you need to practice with those, and those will be part of your exercises.